Bismillahirrahmanirrahim. Welcome back to our course, Deep Learning for Computer Vision. Today we'll tackle a very interesting the field of applications in deep learning for computer vision, which is image segmentation applications. This will be done for sure using deep neural networks, specifically the convolutional neural networks. So let's jump to our lecture slides and start our work. So as you see from the title here, image segmentation using deep convolutional neural networks. The guidelines for this lecture will be, first we'll have some background on image segmentation, then we'll describe and define the types of image segmentation. Then we go to image segmentation models, specifically when we deal with image segmentation using deep learning, and there will be by then some guidelines for MATLAB 2. So what is image segmentation? What is the meaning of image segmentation? In fact, image segmentation is a process or a procedure where we can divide the input image into regions, or let's say segments, to different multiple parts or regions that belong to the same class. So we can say that this image contains 3-4 classes or 3-4 segments, or let's say regions that belong to a specific class based on some specific features. As here from this image that we have at the right-hand side here, or the left-hand side, we'll try to zoom this a little bit. So it's a street with some trees and buildings and cars. While we have on the right-hand side, we have these parts of, or these regions in the image have been segmented into different, let's say, segments or classes. This includes, for example, if you look at here, this is the road with the road signs. Here, another object. Here we have the trees, the tree part here. Here we have the electric polars, etc. So in the input image here, we have the image itself, while here at the output we have a sort of segmentation of the image in this example. So sometimes we may call, or this type of segmentation can be called as pixel level classification, where this involves that in the image or in the frames of a video, we are going to partition the input image into multiple segments or objects. And this will be done on a pixel level. So every pixel in the image will be classified to be belonging to a specific segment or class within the image, having different classes and different regions, or let's say specific regions or classes. What are the types of segmentation? We first start with the semantic segmentation. It's an abstractive type of segmentation where we classify the input pixel into some semantic classes where these pixels will be belonging to a particular class and are simplified as being included in this class. Instance classification. This means that another type of application that can be used to segment and classify every individual object in the image. So in this case, you can, after having the maybe the semantic segmentation, it's a more advanced application or tool where you can give specific class. For example, this is a person, a human. This is a human or person 1, person 2, person 3. If you have more than one person, so you specify every individual, let's say, object in a very, let's say, precise manner. The other type of, the third type of the classification of the image segmentation techniques is the panoptic. In panoptic, we combine or take advantage of the semantic and instance segmentation at the same time. So you apply semantic segmentation, then followed by, let's say, the instance segmentation, where here every sample or every object in the image will be segregated and identified precisely in the output segmented image. Let's have an example on that. Here, as you see that we have this image, you have three persons here on the beach of a sea, and we have some here, we have some, let's say, some zooming here. If you look at this, you can see that some clouds on the horizon. And when we talk about image segmentation for using semantic segmentation, you see that here the classification has been done using three classes. The first class is the human or person, one. Two is the sea, and the third one is the sky, and maybe the fourth one, I missed this one, which is the sand or the shore of the beach. This is in semantic segmentation. Now, specifically in instance segmentation, we try to segment people or human persons, let's say, instantly, so we can say that this person belongs to 1, belongs to 2, and belongs to 3. So we specify every person as precisely and segregatedly. Now, if we go to the panoptic segmentation, here we combine both results in B and in C. So you see in B and C, we combine both results and give this type of panoptic segmentation where you can specifically and very exactly define let's say the objects inside this image segregatedly and accurately. This is a good demo on a video with traffic or cars moving in a road. And here, when we move further, we can see objects that appear and disappear according to their semantic segmentation applied in this case. Another type of segmentation is also followed by object detection and localization. This type is, as you see at the corner here, if you can have a look. Here, let's say this one. Here, as you see, just a moment. I'll try to show you this one and let it run. So you see that the person is 1, 2, 3 up to I see it's 8, and bicycle 1, 2, 1, 2. So and you have some numbers in the surrounding the anchor box at the top of the anchor box, where you can see the probability confidence that we are confident that, let's say, 70% is a person or a bicycle, and this person is 1 or 2 or 3 or up to maybe a large number of people can be identified, detected, and labeled. So this is an advanced tool for the semantic segmentation, which is object localization and detection and localization, and it will be discussed in the next lecture, inshallah. So another example also. Here we have another scene where we have a drone that detects people moving with different, let's say, in a complex environment during its flight. Here it's not very clear what are the classes of each of the, let's say, the purple and the blue boxes, the anchor boxes. Here we call it the anchor boxes. However, we can have a look on the possibility to detect and localize objects within this complicated or complex environment or scene. What are the applications of image segmentation? You can see that there's a very long list of applications. This includes, as we have seen, road applications or traffic applications like road sign detection, lane detection, traffic sign detection. You can find applications in biology, in microscopy, etc. Evaluation of construction materials in buildings, etc. You can have a look also. You can see a lot of applications in case of video security applications and surveillance. For self-driving cars, advanced driver assistance, like in new versions for Tesla, for other self-driving cars these days. Medical imaging applications for diagnosis and decision making in medical applications. Also, you can find in satellite imaging and remote sensing applications. So the list is very long, actually. And nowadays, as if you have a look on the news in the last few months, when you see the Israeli drones are bombing people in Gaza, civilians maybe and others. And this is one of the good examples on using the deep learning in the field of image segmentation, where we can define using these techniques where is the person and what are the type, what is the type that what he's holding in his hands, maybe a weapon, or maybe just he's riding a bicycle, or a bike, or a motor, or a car, etc. Now, before thinking of image segmentation using deep learning, there was a lot of examples on and tools for image segmentation. Just for as a reminder, you can find here different types. We used firstly threshold method applications, region-based methods, edge-based methods, watershed-based methods, and clustering-based methods. And when you go further, you can see a lot of applications here as a classical way for image segmentation. In fact, these applications are very important for sure, but they did not get or reach the desired level of image segmentation that has been done lately using the deep learning applications and approaches. And this is why we moved further and make a big step when dealing with image segmentation using what we call it deep learning applications. Now, DL-based image segmentation, it's a type of segmentation that is based on using deep learning and its tools. Okay, so in this case, the models provide segment maps as outputs corresponding to inputs they are fed in this case. So for each input, each pixel at the input, you can find, or it maps your input into outputs having specific segment or relationship or region of that belongs to it. Usually we have n channels, so every channel represents one class or one segmented class or one region of the input image. So the segmentation in this case may be binary, as simple, either we have an object or we don't have the object, or it could be having more than two channels or two classes. And in this case, we have instead of having the binary situation, we need to fill. So we can have or think of this situation as being multiple binary. So, for example, if you belong to this class, it will be 1. If you don't belong to this class, it will be 0 for a specific class. Let's say class 1. For class 2, the same thing is true, 0 and 1. And so when you stack all these decision maps or classification maps one over the other one, this will give you the n-channel nature or the n-channel classification, which is in more or less can be thought as being filled with ones and empty regions having zeros that doesn't belong to this specific or that class for sure. Now we need here a ground truth map to use it in the training stage. So when we train the network, we need here a ground truth map where we need to set and select for each pixel of the input or each region in the image what is its semantic class or maybe other types of segmentation tools. So this will be corresponding to the following situation. Having a specific class, this means that we need to set to make this as 1, and having it as 0 or not doesn't belong to this class, this will make it as 0. So this can be done by in sort of a binary. It looks like a binary conversion of the input data when dealing with these images. A good example here, suppose that we have this image. Now, this image has been segmented using, let's say, semantic segmentation. If you look at this, you can see the following. So for this part, we have the person. If you bridge this, you can see somewhere this part indexed as 1. This is for the person. So the semantic labels are 1 for person. Next, for the bench, we have 2. Here, the bench. And this will be 2, as here. So this indicates the bench, etc. Plant and grass or grass, and we have a cat. We have we may see the cat here, the corner. Okay, here. So this is the method how we can apply semantic segmentation. Now we call this matrix or this let's say ground truth table or mask or ground truth result as a one-hot encoding. We can now use this way. Can look at the this mask or this ground truth as being a combination or intersection between union, not intersection, union of all these let's say layers, having, for example, the first layer is for the person, the second layer for the bench, the fourth for the plant, or the grass, and the last one for the cat. When you combine all these together, you get one hot encoding map or ground truth table. Okay. Next, we can also, in general, you can say that the model output in an n-channel binary format is known as two-dimensional one-hot encoded representation. What we mean by this, of course, you sometimes may have, for this image, for example, in the situation for this one, you may get this matrix as a ground truth table. It could be just in terms of a file having details about these 4 classes as CSV format, .csv format, colon separated variables or vectors, and you may sometimes also have it as an indexed image with values 1, 2, 3, and 4 inside this image. So if you look at this image, you'll feel that it's dark. However, when you read what is inside, it's indexed type of images that can be used as a ground truth table, for, let's say, having this one hot encoding inside it. Okay. Now let's go. One of the good attempts is the encoder-decoder configuration used for semantic image segmentation. In general, this is the block diagram of the encoder. If you look at this part here we have the inputs. Here we have the inputs from the image or maybe the data. The encoder network will be working on performing a feature extraction and feature definition and let's say saving. Here we have some intermediate stage where we get only a sort of code for the whole image, a very condensed code, having all details about the features and the segments in this image. Then we go back in the opposite direction and extract these features to be classified into some objects or regions at the output. So this is one of the ways that we can represent or understand what is the what we call the encoder-decoder type. Now, if you look at this image, the same thing is done. Now you can think about the encoder-decoder, let's say, a type of segmentation in the following manner. When you go from the image to the first stage, which is the encoder, here we try to compress the spatial information and compress the spatial information and increase or condense the let's say the feature information about this image. This usually can be done using max maybe or maybe average pooling. So by pooling applications, you can compress the spatial domain. And having these pooling indices, you can build what we call it here the bridge or the bottleneck, because we have a sort of this is its size, and we go down, down, and then go up. So in this direction, we reduce the spatial. It's a very straightforward application of convolutional neural network. You can replace or can substitute different types of neural networks at this scale, at this location, and this can be, for example, ResNet, can be if you want RxNet, it can be DenseNet, etc. And this usually is called the bottleneck. Sorry, the backbone. The backbone. Okay, backbone. Now here at this location we have what we call it the bridge or the shortly the bottleneck. I'll try to. Okay. And here the operation will be opposite. What is the main idea behind these things? Now, when you compress the information in this direction and increase the feature maps, and you then extract, apply opposite operation, in between you are getting rid of, let's say, not of the information that's not very important for you. So you concentrate on the main information inside this image, and this will lead to get at the output different classes having these images. For example, the here they have the road, the buildings, etc. So what we can do this way is to compress the spatial information, increase the feature information, and applying this in the opposite direction in order to get the same size as the input size, and by extracting and giving benefits to the let's say the what you call it the feature part of the image. Now we can use for the backbone different types of networks. This can be done at this location. Okay, this will be opposite to it in the other direction, and in between we are concentrating on getting the best representation at this location, or sorry, this one. Let's remove this. So this one represents our intermediate stage, which is the bridge or the bottleneck, where we condense all the useful information about our classes. And this will be controlled and prepared by or enhanced or applied using or having the ground truth for the input image. At the training stage for sure, then you can apply this at finally at the okay. Of course, here it's very important to note that this type of encoder decoder configuration and the semantic segmentation is done without, it's an unsupervised technique. So during your operation, you are not asked to get the output can be any value. So you cannot from the beginning know, you don't have labeled data. You just have labeled classes instead of labeling the data itself. So this is why we can say that it's an unsupervised learning tool. Now, this is a summary of what we have just said in this block here. Okay. Another way to represent this, we can look at this block diagram here, or the block flow chart. So we have the input image. This is the encoder. Here we have this is the encoder, followed by the bottleneck, where we have the latent space representation, which is the very condensed representation about the features in the image. Now, once we get this, so meanwhile we have lost a lot of unnecessary details, then we extract this data in this direction to get the constructed image, and this case will be labeled with different classes, or maybe just with binary classes, only two classes at the output. This is the same concept, the same image. So what we can say now, that this is a type of what you call it encoder decoder or autoencoders. It's a type of neural network architecture that implements an encoder and a decoder. We said that the encoder is used to compress input into lower dimension representation with higher feature details and lower spatial details. The decoder is used to opposite or to apply opposite operation to the encoder, and this leads to the fact that we are dealing with unsupervised learning accompanied with the pixel-based classification. So we classify every pixel in the image and whether it belongs to this class or that class, and this is why we you need the truth table or the ground truth, let's say map or table or matrix to help us in defining the output class for this or that pixel. The proposition of the encoder decoder was done in the SegNet network, and in this case, if you look at the image here, this is the input image at the left-hand side. We have the RGB image, as you see here. Okay, here this is the input image applied to the encoder part, then decoded using the opposite operation at the other side, and this is the output with getting the results of segmentation. If you look at the colors here, we have this blue block, let's say, or matrix, represents the convolution plus batch normalization plus ReLU. So it's a block of conv plus batch plus ReLU, followed by pooling. Followed by, if you look at the pooling, you can see somewhere here we have the pooling operations. Here we have upsample, and here we have somewhere the pooling layers. The pooling layers for the application. So in this case, we apply max pooling, we reduce the size, where we have the upsampling at these locations to oversample or to increase the sampling and increase the size of the image or the spatial domain or the spatial features in the image. Finally, and the last, we have this softmax layer. If we have more than two classes, we use softmax. We have two classes, we just use the sigmoid function representation. So in this case, we have SegNet. It implements a convolution plus max pooling to downsample and to squeeze information into a bottleneck. Then the decoder reconstructs from this bottleneck. It highlights the regions where the input has a specific class and put them in or order them and group them in classes. Here we have, if we have just two classes, we use segment activation function. Otherwise, we use other types of segmentation activation functions like the softmax activation function. Another type of semantic segmentation tools in deep learning is the UNet. In UNet, the main concept, maybe the main concept in UNet over the SegNet and the autoencoder networks is that we bridge or we connect the input to the output at this location for all layers in the encoder and decoder. These connections are called the escape connection. They are very similar to the escape connections in the ResNet. Here we try to transmit or send the information from the input encoder to the decoder. This is in order to improve the quality of the output image and keep or get a sort of residual information about the output to get it in classes. In general, this is the UNet construction or architecture. Let's have a look on what are these things. Of course, you can see 1 layer, 2 layers, 3, 4, and the bottleneck or the bridge. So we have 4 layers with plus the bridge, and the same thing for the decoder. So if you look at the network, you can construct it in the form of a U letter. So this is why we call it the UNet, because it has the shape of U letter. This path represents the path where we try to compress the spatial information and get feature information and squeeze the features into the bottleneck or into the bridge. On the other hand, we have an opposite operation to expand, which is the expanding path or the decoder path, where we have their pure or clear version of the main features of the image after compressing them in the encoder part. Okay, this is the bottleneck or the bridge that bridges the two out, where we have very condensed, squeezed information about the features in this image regarding the classes for sure. And here we have what we call the skip connections. So in the skip connection, we take from every layer, maybe the first, second, third layer, fourth layer, we transmit the value obtained here and concatenate the output or the input coming from the encoder with the output obtained from the previous layer in the decoder. So we apply here a sort of concatenation. If you look here at the symbols used in this case, you see that this arrow, convolution plus ReLU. So this one is convolution plus ReLU, convolution plus ReLU. Here, the skip connection is copy and crop. So we send from encoder to encoder the same layer. We use here just add or concatenate, and we need copy, what we call crop and crop. Copy and crop is just to keep the compatible sizes between the concatenated layers or channels. Here we have max pooling by a factor of 2. So this is max pooling. It's max pooling. So as you see here, the size was 128 for the channel. We doubled the channel and reduced the size for the image. So we have here a size of, for example, 285, and the after reduction we got as 140 because we used max pooling with a factor of 2 by 2 or size 2 by 2. And so forth. So you can see that the size of the image is very large here. It's just one class or one channel. Then the number of channels is increased, and the size in the spatial domain is decreased until we reach the bridge, where we have here, as see here, we have a bridge of 1024 channels having feature information and very small spatial domain size, which is 30 by 30. Now, on the opposite direction, we have we apply oversampling, or let's say upsampling, as see here, to improve or to increase the size of the spatial domain and convert the data obtained from the feature maps into the. Let's have an example here for, let's say, this one. Let's say and look at. Let's say the following. Now we have here the input. This is, for example, the size 100 by 100, and with a channel number 256, we apply upsampling. The size will be 200 by 200. So we upsample this, instead of having 100 by 100 to 200 by 200 pixels. And the number of channels was 256. It has been reduced to 128, and so forth. We repeat this process until we reach the latest output, where we get, as you see here, we have the output is having here 2 layers, because one for each, let's say, for each of the classes, and this is the output size of the image. After that, we apply the segmentation map and get back to the original image and give each pixel in the image a specific class. What is the main purpose of the, of course, for the skip connection has been introduced to avoid the loss of information observed in downsampling layers. So when you downsample an image, for sure you get some, let's say distortion or loss. Now, sometimes you may require this data at the decoder side. For this purpose, you can just bridge the input to the output, or from the encoder to decoder, in order to keep or to follow the original data. This will help you in finding the images in classes as a result of applying these skip connections. So they go, of course, from the encoder to the decoder without passing through the bridge or the bottleneck. Also, you can concatenate in the decoder these according or to the use or the usage of the skip connections. You can apply and get some concatenated information or between the spatial and the feature information as a source of go forward and backward between them to obtain the best solution in this case. It has for the unit has a lot of applications, including biomedical imaging tasks. Now it has been implemented in a very large uh, and a wide variety of applications, including electrical, communications, engineering, etc. Another issue is that it can handle large images with a very quick application because the training is not here very complicated. It takes a lot shorter time for processing, and you can apply this if you have a good GPU. You can do it very quickly. Once you design your system, you can check for its performance directly. This is what we can see for the unit. Now we have different types of unit. Now the base or the plain unit. Then we have an extension to 3D unit in medical applications. Attention unit. Here we have attention mechanism to concentrate on specific parts of the image. Inception unit. It implements the concept of the inception proposed in the VGG and GoogleNet. Residual unit coming from ResNet, where we can use the backbone in the encoder and decoder, specifically in the encoder, using the ResNet basis on a ResNet basis. Same thing for DenseNet, where we can use DenseNet to aid or help in improving the quality of the unit by replacing the bottleneck of the plain unit by a backbone taken from the DenseNet. You can find other versions like Unit Plus, Unit Plus Plus. All these versions are based on using the unit structure by replacing this or that part, or that part, and by substituting some bottlenecks and maybe some backbones. You can use all these topics and improve your unit system. This is a medical application for the unit. I see that mainly I'm not going to go deep in this. This is the object where we get some tumor. And here we can classify the tumor into more than one region. And finally, we go further to obtain different classes. As you see here, we have a lot of classes of the tumor tissue with different levels of problems. Here it's glioma subregions, and this will help or aid the medical staff to work properly and specifically to deal with these problems, either by surgery, maybe, or by medications, etc. It's maybe a little bit out of our scope. However, it has a very strong and deep and very intensive implementation and utilization in the application of medical imaging topics in medical applications. Another application maybe in maybe satellite imaging or drone imaging. On the left-hand side, you can see that here we have areas of rocks, and some parts are with plants and with maybe vegetables or maybe other products, maybe here agricultural products for sure. And now, if you look at the image using here at the in the middle or in the center, you can see the vector labels. So these are the labels, and here we have at the right hand side we have the output obtained as a result of the unit application of this image, where the yellow region means that we have grass or maybe we have crop, some crop that we can harvest maybe, and for the dark area we have no crops or maybe no plants there. And this is why how we can implement this for different applications, as in agricultural applications, in electrical, medical. In electrical, you can use it and find, for example, for fault detection, for operative cells detection, etc. All these things can be found, can find application in this field. Now you can see different examples on the unit application in electrical engineering, plus a MATLAB link here for to see how you can use the unit in MATLAB. Hope it was enjoyable for you. Here we have other links also, how to understand and to work with the unit, with the autoencoders. And I think this enough for today. And that's all, talks. I hope that you enjoyed this lecture and hope to see you on the next last lecture for this course.